Well, this tutorial is going to give a basic introduction to volumes in Houdini. You're most likely to come across volumes if you use the volume-based tools for smoke and fire, which are available on the shelf. And you don't need to know a lot about how Houdini handles volumes to use these shelf tools, but a basic grounding can be useful. So let's start by creating a volume without using the shelf tools. I need to lay down a geometry node, dive inside, and delete the file. If I then hit the tab key, I get a list of all the SOPs that are available, and there's a menu at the bottom that deals with volumes. The most basic way to create a volume is using the volume SOP. Let's lay one down and have a look at its parameters. The first parameter, rank, lets you determine what kind of values the volume is going to contain. As we will see later, if you choose vector or matrix, you're in fact going to create several volumes, not just one. Next comes the name. Now a volume is really just a way of storing an attribute, a floating point value, that isn't fixed to a single point or primitive, but varies over a space occupied by the volume. If you leave this name blank, the name defaults to density, but it's often better explicitly to name your volume, so I will call this myVol. Then we have the initial value. I'll give it an initial value of 0.5, and we can see that it immediately appears in our 3D view because the volume is no longer empty. That is, it no longer has a value of 0. The viewport is just an approximation of the volume. Areas that are thicker indicate higher values, and those less thick, lower values. In this case, of course, the value is the same throughout. Then there are parameters to adjust the size and the position of the volume. We then get to the sampling parameters. Of course, if we have an attribute varying over the area of the volume, we can't store the value in every place. We would need to store an infinite number of values to do that. So instead, Houdini stores values at fixed points, and then, when needed, calculates the values in between using interpolation. So it divides the volume up into a series of boxes called voxels, and stores a single value in each voxel, or more precisely, at the center of each voxel. These sampling settings determine how many voxels there are in a volume. In general, it's better to have voxels that are regular cubes rather than non-square. At the moment, our volume is the same size in all directions. So if we middle-click our node, we can see that the volume has 10 divisions in each direction. If I increase the height of the volume, we can see that because we have max axis set, the max axis is Y, and that ends up having 10 divisions, while the others have less. As I mentioned earlier, each volume can contain only one varying float value. Let's confirm this by changing the rank parameter to be a vector. Now, if we middle-click, we can see there are in fact 3 volumes. We can't see them because they're all overlapping. It doesn't matter that there are overlapping volumes. Mantra can perfectly happily render volumes that overlap. Indeed, this is central to how it manages complex attributes. And if we bring up a details view and look at the primitive level, we can see that there are now 3 different names for our volumes. Let's change that back. Volume SOP is rather dull because it simply creates a uniform volume. A more interesting way to create a volume is by converting geometry. Let's lay down a sphere. If I want to turn this into a volume, I need an ISO offset SOP. By default, this doesn't create a volume, but an ISO surface, a particular kind of mathematical surface. But it's much more often used for creating volumes. We can choose to create a volume using the output type setting here. There are 2 ways to represent an object as a volume. The simplest, which Houdini calls fog volumes, is where each voxel that is inside the object is set to a value of 1 and those outside are set to a value of 0. As we can see, when we select this, we get a sphere-shaped cloud. There is another way to do it, which is called the signed distance field, or SDF for short. With this, the value stored in the voxel is the distance from the center of the voxel to the nearest surface point. We give this distance a negative value if the voxel is inside the surface, and a positive one if it's outside. That's why our visualization shows the sphere as missing. All the values inside the sphere are less than 0 and so don't show up. The mode parameter determines how the node goes about its calculations, with different options if you're trying to build your volume from a set of metaballs, a group of points, or another volume. You might ask why you would want to build an ISO offset from another volume. Well, one reason is in order to downsample it. In other words, move from having a very high number of voxels to having a lower number of voxels. Then we get to the sampling options, which we're familiar with already from the volume SOP. The offset parameter allows you to build the volume slightly offset from the input surface, as you can see. The rest of the parameters are rather technical, and you only need to change them if your object is not being correctly converted into a volume. The most common problem is with laser scan. If you have some geometry which is very concave, for example a bowl or a cup, the inside may not be detected properly if you use laser scan, and it may be necessary to turn it off. Finally, you can save out the volume you've produced to a file. This can be useful if you've got a very complex object and a very large number of voxels, in which case the ISO offset can take a long time to work. Another way to create a volume is using the ISO surface node. This is a bit like ISO offset, but it doesn't really take geometry as its input. In fact, it does take geometry and can use that to set the size of the volume and draw on the values of the volume, but that's a rather complicated issue, and it's better to look at the help card for that. So instead, mainly it takes its values from a formula which is set here. $x, $y, and $z are simply the position within the volume. So, for example, I can write noise $x, $y, $z to create a volume that is based on noise. I need to check the fog volume box here to get it to produce a volume. Note that this is producing a standard fog volume, not a signed distance field. Another thing you might want to do is to change or combine volumes. You can use a volume mix node to do this. It has two inputs. You don't need to use both, in fact. For example, if we just have one input, we can set the mix method to user. This allows us to tweak the values inside the volume using the formula here. $V is the existing value. So if we say $V times 0.5 to make all the volume values half as big as they were, we can see that reflected in the viewport. But importantly, you can also use it to mix volumes. So let's connect our sphere to one side and the noise to the other, and choose multiply. The result should be noise that exists only within the sphere.